I'd expect you to know what technique to use, depending on what the situation is.
So could you give us some examples of each? Maybe? I know it's giving away the game, but...
No, I don't think it's giving away the game.
Okay.
I think this is what you should know. You should
Yeah,
know
I
if I
know.
ask this question, this is what you should
This
do.
is why I need a study.
Yeah, don't think of the test as trying to trick you. I don't read it
Okay.
that way at all.
Okay.
Here's the level I expect you to be at. You guys, it's not a very good question because I think it's easy. But I'm just attacking the issue of what's being meant. Oh, hold it, you guys. I made a mistake. Just a minute.
So with subject 2, that's obviously Lagrange, right?
I disagree. I don't think you can talk that fast. I'm sorry for going so fast. I just want to make sure I get through today's discussion. So I try to hold things to the end. But you asked. You guys help me with this. Second derivative test? No, second derivative test for local extreme. That's that question. So here you use Lagrange multipliers because I think this is just a curve in the xy coordinate plane. So I'm trying to optimize some function in free space subject to just a curve in the xy coordinate plane that screams out at me Lagrange multipliers. I think if I asked you to find max and min values of this thing subject to this constraint, well, jeepers, that's not a curve in the xy coordinate plane. That's a whole region in the xy coordinate plane, meaning its boundary and the interior points. Okay, now that we realize what technique we're not using here, tell me how to answer the question. Make full sentences. You know, Friday fails exam.
Use the second derivative test to find the local extreme on the inside of it.
Perfectly put. He's saying use the second derivative test to find local extreme on the inside. And you don't have to actually use the test fully. Just find the critical numbers or critical points in there. But then you're also gonna test the boundary, which actually is on the corresponding
That thing.
You math D experts on that.
Circle. No, it's an ellipse.
Thank you. Are you there?
Did somebody actually say? I swear to God, if it's
Oh, so
Yeah, I heard an ellipse a couple times, yeah.
Well, Catherine, you talk softly. I'm hard of hearing.
So that one you use the second derivative test to find the critical or max or min, whatever it's going to be.
Those are the only
For number 2.
Yes.
2. Wait, the second one's the second derivative test.
Yes, and then that was the derivative test, that was boundary.
Matthew, this is not just a second derivative test. You use a second derivative test to find the critical points on the interior, but you also got to check the boundary. But that resorts you back down to math 30. Matthew, am I making sense?
Yeah, I'm just gonna have to do more homework. I've studied for like 4 days and I need like more time.
You studied 4 days of this class?
Yeah, because I was studying for physics before and then.
Oh, you're switching on.
Yeah.
So repeat that again on the second.
On the
Yeah,
second
this is important. I mean, if I were to answer this question the way it's asked, I would find all critical points on the interior of the curve. In other words, all critical points within that ellipse. Now, you don't have to fully use the second derivative test, do you? All you really need are the critical points. Put them off to the side. Optimize now this function up here, Linda, on the border of this elliptical region, which is actually on this equation.
So the second part would be with the Lagrange multipliers.
You know, you could look at it that way. I typically just use my math 30 skills.
Okay.
And then evaluate the original function or that function at all those critical points. And at the interesting points you saw down here, and see which one's the largest, see which one's the smallest.
So, would these be, so the second one, obviously, you would just use a second derivative test, find local extrema, to determine the
Yeah, I
local
think it's
extrema.
clear
It's
you
pretty
wouldn't use
straightforward
Lagrange multipliers,
with that,
that's
right?
strange.
Yeah. Would this be basically like the kind of variety of questions that we would get, or is there anything else you could think of that, other way of phrasing these that we're not seeing?
Yeah, I could use words.
You could use words.
Oh.
Like
it's a
intersection
box,
or something?
Free space with a fixed, square, surface area.
Now,
And
so-
can you maximize the volume of surface area?
Some of the box problems were some of the ones I was having like a little issue with in here. I was hoping maybe we could cover one of those today.
Oh, yes.
Like I have a really good one
No,
that
no,
you could
yes.
solve with both
The box type
optimization
problem is
and
actually the problem
Lagrange.
in that I don't think it's just that obvious in how to solve this system of equations. That's where the problem's gonna come in. I
Well,
can see it in my head.
Solving the system, it's actually kind of setting it up. I was having a bit of an issue with the girth. I think, Catherine was telling me that it's just going to be the size of the perimeter of the base.
That's the only way I could think of using the word depth, but they
But
say
I'm not really entirely sure what they mean by girth.
Isn't that just like
I'm looking at the, what I'm trying to
So I
think.
think that would be like the volume of the base,
Because you
right?
have
Just
to
the
use some
girth,
word.
but,
And we're still limited time.
yeah, I know.
I'm stalling, looking at the clock, thinking, what's going on tomorrow? Because tomorrow's Halloween. I just don't know how tomorrow's gonna develop. It might be the case that I can still stay really late.
Stay really,
Or you guys,
we're not even here tomorrow.
well, I just meant the math.
Oh, in the math center? Okay.
Yeah, I'm being available.
For a box type problem, we need some like service area constraint, right?
Well, it's some kind of constraint, yes. I just don't want to blow up a box to an infinite volume. I just think, whatever.
I had a quick, can we do 56 on 11.13.2? Because like they did some weird algebra and
13 what they did.
Or 13.2. Are you sure it's 56 or 57?
I think it was here.
Because 57 is the scary one.
Hold on.
57 is the one I looked at.
56 and 55 are like I couldn't integrate it, but
Oh,
after I
55 is easy.
integrated it,
Alright, you guys hold off, I'll see if we have enough time to end class. I put it up there, so I remember.
Okay.
So you guys check this out, some unfinished business I did not discuss last time. X-axis. Sorry, I won't change things.
What should
I
we title
meant-
this?
What's that?
What should we title?
Still looking at double integers.
Oh.
I just don't feel like I did a lot of examples last time.
Nope. I was agreeing with that. See you guys. Hey, so are we still on, are we at 13.2?
Yeah, can I just throw some unfinished business from 13.2? You know, when you take a peek at that region down in 2 space, what if I already compute the volume of the solid in 3-dimensional space that's created by taking this region and moving it directly 1 unit up? Now, to compute the volume of this region, wouldn't the volume be nothing more than a double integral? Evaluated over that region R, and I'm going to integrate with respect to area, but I got to put in the function f, which really is the upper bound, the top of this particular geometric figure. And when you look at the surface on top, what is this equation? Z equals 1. And so I think that is the integral.
Wait, what?
I think it's just the integral, the double integral over that region, and I'm integrating with respect to area.
Okay, now say that one more time.
Yeah, this is
Quarter
important
speed.
because I'm not finished. I'm not finished.
Okay, well, I'm
Would
gonna
you not
stop.
agree that if I just look at the plane, whose equation is this? And I want to find the volume in between the xy coordinate plane and this plane, but over that region R. Am I not just trying to find the volume of this 3-dimensional object?
Yes.
Everybody okay with that?
Yeah.
Because I'm going to change it. Because that volume is the same as don't yell at me, it's the same as the area. Think about it. 1 dimension's 1. When I take away the dimension, when I take the volume, divide by 1, I get the corresponding area. All I'm suggesting is that I could use double integrals to determine the area of a region in just one-dimensional space.
Because the height is 1 unit.
Because the height is 1 unit.
This is why this works.
Yes, I can interpret this evaluation of double integrals, either the volume of this thing in my picture, or just the area of the region R on the xy coordinate plane. So keep that in mind.
But isn't that only if it goes up 1 unit? What if it goes up like 3 pi units?
Well, that's why I'm saying now, whenever you look at a double integral like this, integrating with respect to area, and you see a 1 in there, you could interpret that as the area of a two-dimensional region. Or I could be sophisticated and ask you guys to use double integrals, compute the area of a two-dimensional region. Give me a few minutes, I will.
Wait, isn't that the same thing you just said up there?
Yeah, it's the same thing I just said up there.
Like,
Specific.
So,
What was that?
That seems really specific situation. Only when it's 1 unit.
You know, I don't know, I think it's kind of goofy. I think it's goofy in the sense that I could have just asked you a standard math 30 question and say, compute the area of this region in two-dimensional space, no big deal, or maybe it's beginning at 31, excuse me. I'm just saying I could use double integrals to do the same thing.
So, in 31, because we got the area under, like, it was the area bounded by 2 things.
Yes.
It was kind of funky.
But now that's the region I've got in the xy coordinate plane.
Yeah, so, like, instead of, like, doing all that fun, you just do, so you just integrate x and integrate y, and then, like, 'cause as long as you have the 2 functions that you're bounded between,
Yes.
that's it. You're done.
But don't take this the wrong way, I still think there's some amount of work involved.
really?
Well, sure, because think about it. Once I actually evaluate this thing, if I'm going to integrate with respect to y first, then with respect to x. If I integrate from, I don't know, a to b, and then one function f1 of x, and f2 of x, then once I integrate, don't I immediately get this?
Oh, that's true.
Oh, shoot, that's how you set it up back in math 31. Same thing.
So, like, I guess this is a dumb question, but
There are not dumb questions, man.
why do you have to do the functions first before the constants bounds? Like, could you just?
Here's why. It's because typically speaking, if this is the x-axis, here's the y-axis, I do need to talk about those boundaries in the y direction. So if I'm going to compute the area of this region right in here, using a double integral, and if I'm going to actually integrate with respect to y first, then when I draw my upwards arrow, I got to talk about uppermost extreme and lowermost extreme for y's. Oh shoot, you know what? As I slide this arrow from left to right, upper and lower extremes change, they're not constants. And that's why integrating with respect to y first, I really do need to have these boundaries for the y function, which are not constants. They could be. I could be integrating over a rectangular region, but they might not be.
Okay, so that's why you do the constants first before the, not the
You
functions.
do the functions first, that's on the inside interval. Now, I also maintained back in math 30, you guys looked at the average value of a function by doing what? Over some interval from a to b, what did you do?
The integral and then 1 over b minus a.
So can I just do this for you guys? I think obviously then, if I'm looking at the average of infinitely many y values of a function in 2 variables over some region R, I think likewise it's just going to be the evaluation of a double integral over that region R, evaluate on a function f in terms of those 2 variables. Oh, but like I guess I did back in math 30, I'll multiply on the outside by 1 over the area of R. Same idea. 2 small tidbits that I didn't mention last time. I'll leave it for you now. Because what I would do next is I want to start talking
Say in the denominator?
the area of R.
Area, oh.
And R, by the way, Linda, is this region right here over which I'm integrating. It's the same R.
Oh, you're getting ahead of me. I'll still write that down.
I know, but I wrote too sloppy and she's asking.
I was told that the integral s actually was originally an f for a function, but it was written in script. Is that true?
I have no clue. I have not heard that.
guess that's what Stephen Jones said.
So what did he say specifically?
He said that the S was originally an F, but they wrote in script, and just over time, we lost the little line through it to make it an F, so it turned into an S,
And F came from?
a function.
That does surprise me. I hate to call this process a function, because you're used to think of functions mapping numbers to numbers. As a mathematician, I typically think of a functor as mapping functions to functions. But I wouldn't use the word function.
Okay.
Interesting.
It could have been functor, because I'm what is it, second generation knowledge in here?
Oh, I think the word
Someone told me.
functor has got to be an extremely recent word.
Okay.
Yeah, category theory is a subfield of mathematics. It's very recent.
It must have been function.
Or maybe it was something else.
What if I did something different, you guys? X-axis, Y-axis, and I want to integrate over some region. It looks like this. Very special type of region. That kind of reminds you of
It looks like a piece of pizza that somebody took a bite out of.
I meant mathematically.
Oh, okay.
Polar coordinates? Because maybe I could take a theta value that's, I don't know, how about the theta sub naught? And the theta value that's theta sub, I said,
Say again.
And I will subdivide that amount of rotation into n subintervals. And maybe I can even talk about an arbitrary little piece right in here. Actually, you guys, I can't. It's too small. Can I blow it up? Does it look like that? That's the thing I got shaded in over there. And I think if I'm going to integrate with a double integral over some region, some function f in two variables, and I'm going to integrate over area, which is this big region, big R, then over just one of those small pieces, let's see if you and I can't compute the area of that one piece. Maybe it would be like, I don't know, length times width, or what do you think? How about this? Do you guys agree that this angle is simply a small change for the angle theta? Whereas I think this over here is merely a small change in R. And if I were to take a peek at the length of the arc out here, wouldn't the length of the arc out there be nothing more than a radial distance? It's called r sub I, times nothing more than the measure of that angle. You guys got to be honest with me. Just back in trigonometry, isn't that the way you compute the length of an arc? I ask for honesty.
Yes. Sure, still writing it down.
Yeah, so the arc length is nothing more than the radius of the circle times the corresponding central angles measured. If that's the case, shoot, you guys, I think that if I'm going to rewrite everything in terms of polar coordinates, I can rewrite this as the integral of a function f in terms of x and y.
R's and thetas.
R cosine of theta? Comma.
R sine of theta.
I'm getting nervous. Times, or excuse me, dA, which is oy, oy, oy. Okay, if I multiply the arc length, that's right here, times this length right here, and I take the limit as n increases that bound, does this become a d theta? This becomes a dr. Oh shoot, but I've also got an r. Well, r sub I is an arbitrary r value in that particular piece. It's not really standing for initial r value.
That's what it means.
So I think my dA becomes an rd theta. And I'm going to integrate for, say, one function in theta to another function in theta. And then integrate from one extreme value for theta to another extreme value for theta. It's simply just a different way to value double integral, nothing more. And I refer to this as using polar coordinates to value double integral.
Why do we care about that big area and then all of a sudden we're a small?
Because I'm skipping a line. Technically speaking,
Why do-
I think the area right here might be considered just simply this thing right here.
So you actually assigned some homework on this stuff, right?
I did.
Already? I think so. I remember having to, I think I had to pull into Polar a couple times.
You know what, if the author said
Or I might
that-
have just pulled into Polar just to make it simpler, but,
That, or maybe the author asked you in this particular case, use pull corners just to give you a heads up for the next
Okay.
section. Maybe that was the case, and I
Thi-
didn't really look carefully.
this isn't gonna be on the exam though, right?
No.
Okay.
So Maddie, can I come back?
I guess one more question is like, why does it matter? What kind of question would you be asking? Why do we care about that?
Okay, you ask. I'll start my exams.
Oh.
So, like, let's say just for fun, can we convert back to rectangular coordinates with that?
And you know, sometimes you might prefer to, I mean, if you end up with an integral where it's easier to evaluate in terms of rectangular coordinates, absolutely. Oh, excuse me, you guys. Guys, I'm too tired today. I can cheat and not make things up. I made some examples. Oh my goodness.
Is that our quiz? Is that a graded quiz?
Did you give me a quiz today?
Yes, we did, and if you haven't done it,
Really?
yeah.
Yep.
We gave it to you on Monday. I wanna say that makes 5 or 6 right now.
You
I'm
know what
pretty sure
happens?
it's 6.
I taught Monday night, but I also had to go home and grade a full exam for DE.
Yeah, I saw
And
it.
so that's why I'm really sleep deprived, I apologize.
That really sucks. Like, that really sucks. You know, you're gonna say it's multiple choice.
That wasn't even funny. You know, we had full-time faculty member recently did a multiple choice test at 30 or 31?
I think you said it was 30.
30. Multiple choice final exam.
That's not.
Bye-bye.
Gosh, those poor students when they got the math reached 31.
No lie.
I did an algebra 2 teacher that did that.
Here?
No,
Okay.
in Ohio.
Okay.
You're from Ohio?
No, I moved there and then I moved back.
Really?
Yeah.
That explains a lot.
Oh my gosh.
Here's what I'm seeing.
I have to confess, if I tell a story about Connecticut, I have to ask class of anyways from Connecticut. Don't hurt anybody's feelings.
Well, if anybody was from Connecticut and they live here now, then you can't hurt their feelings. Because
Why would you say
place is
that?
so
I
awful.
lived in Connecticut for 6 years.
Dude.
The place is awful, why not? It's cold. Oh gee, let's not heard about this.
reason.
So you guys, in this example, here's an example where maybe, now that I'm writing the board, I don't have to use polar coordinates, but it certainly fits it well. Because I think in the integrand's position, only because you guys are experts in polar coordinates from math,
A.
8.
A, 29, and 31.
Those
We said A, I meant 8, 29, and 31. Then another name for what's in the integrand's position is just r squared plus 1.
Is that D or?
Yeah, I meant this to be a D. So I'm integrating over this region D.
Because we used to have all this R and that's just.
Now, you guys, here's a circular region, the xy coordinate plane. Somebody tell me how the r values change. 0 to 4. When I span out that circle, the r values, did you say 4? You meant 2. 0 to 2. And by the way, when I span out the circle, that region D in the xy coordinate plane, theta ranges from 0 to 2 pi. Does everybody agree? Everybody.
No.
What do you mean no? Why not?
DYDX.
Yeah, I can't use dy dx. I've written everything in terms of polar coordinates. I have to write, is it dr d theta or d theta dr?
R, D, R,
It's neither. It's r dr d theta. Do you guys agree?
Um,
I get,
can you explain that?
I get where you get the, like the 2, because that's the radius of your circle thingy, but where do you get the 2 pi, or is that's because you're integrating like in a circle?
Matthew, maybe I should have drawn a picture, I'm sorry. When you look at this region D in the xy coordinate plane, it's really this region right here. I just think to span out this region, any ray emanating from the origin is going to have the quality that radial distance starts at 0 but ends at 2. And so I think our range is constantly from 0 to 2. There are no functions in this case. Well, the functions are constant functions. But also to expand out this region, I have to rotate from 0 to 2 pi. That's why these are the bounds for the theta variable. And you guys have to agree, this integral is going to be an absolute piece of cake to evaluate. Brad, were you asking me for the r d theta distance?
Yeah, I want you to explain that.
Because I think the r d theta is nothing more than the length of an arc in here for some r value called r sub I. So I think the length of this arc in blue is nothing more than what you see inside that circle. It's just this length right here is, what you see inside this circle.
Okay.
And so I think my dA, after I take the limit of a Riemann sum, becomes a limit of a Riemann sum involving r sub I delta theta delta r. I just wrote it as r dr d theta since I took the limit. So when it comes to polar coordinates, you necessarily have to have that extra factor in here.
But
If you're
you're,
going to convert to something else called spherical coordinates, gosh, is that on Monday? Then I think it's going to be something completely different.
but you're treating r though as a variable.
Oh, it's definitely a variable. Look,
Okay.
I'm integrating respect to
Okay.
r first.
Okay.
Absolutely.
Can you switch like in XY coordinates? Can you switch to your like order?
You can, it's just so often when it comes to polar graphs, you're given r as a function of theta. So more often than not, I think you're going to be integrating respect to r. I shouldn't say more often than not. You're typically going to integrate respect to r first. You guys, can we finish this real fast? It's so easy, isn't it? I've got the integral from 0 to 2 pi of, is that a 1/4 r to the 4th? Plus 1/2 r squared.
That's what, 6?
That's a 4.
No. The total value. And then you're integrating that.
Good, I agree, I'm a little slow with my arithmetic. So we're integrating 6 with respect to theta. But that's simply going to give you a 5. I agree. Now, what does this really mean? I don't know. It depends on interpretation. You could say this. Consider the circular region in the xy coordinate plane, and look at the volume underneath the graph of z being equal to this garbage over that closed region D. And this number right here is the corresponding volume of the solid.
Okay,
It's just a geometric interpretation.
How do you conceptualize that? So
I'm saying you can interpret the actual question as being this. Consider the surface z being equal to this in the xy coordinate plane, and compute the volume underneath that over this particular circular region in the xy coordinate plane. So it's sort of like a cylinder with a not flat top.
okay, but then wouldn't it have an infinite surface? I mean, an infinite z value? Because if it's this, but we're setting the bounds right there.
Well, no, because I think z being equal to this garbage, graphically speaking, represents what?
Yeah.
Well, this time it's going to be circular parabola. And so I think I've got a container that's got an elliptical top like this and going straight down. So you can interpret this as the volume of that three-dimensional object.
Yeah, but I was saying between those 2 points, 0 and 2. Is that what we're saying? Or, like, how do we know when to close the z bound, I guess is my question.
Oh, it's very clear.
Well, not
You-
for me, that's why I'm asking.
We take a look at the boundary down here, which is a circle of radius 2, goes straight up to the paraboloid, and that's what seals it off.
Okay,
It's really because of the boundary that curved down the xy coordinate plane.
Okay. That's good.
I'm sorry, but like, from when you went from rectangular to polar, because the thing is giving the rectangular coordinates, so you have because you have the circle up there given by x squared plus y squared equals less than or equal to r, so that's where you got the like 0 to 2, right? But how did you get r squared plus 1?
Well, I was simply suggesting that another name for x squared plus y squared is r squared. Back in trigonometry, when you look at polar coordinates, here's the x-axis, here's the y-axis. If I look at a point x comma y, you guys remember what polar coordinates are all about?
No,
No.
kind of missed the chapter in 31.
So, I'm in New York City. I want to move from there to here. I hail a taxi cab, sorry. I hail a taxi cab. Isn't a taxi cab just going to drive me along the street in a very rectangular fashion? And I might consider this location to be nothing more than A comma B, where I'm traveling horizontally A units and vertically B units. But what if I stepped off the curve and I wasn't looking, and the taxi hit me? And it killed me. And I still wouldn't go from here to here. Would I walk in that direction? No.
You'd be dead.
I'm dead. So I probably look in the appropriate direction. I'm gonna call it theta. And just walk a certain distance. We'll call it R. And I think it's just a different way of getting the same location. I think the location would be located R comma theta. If you guys don't mind in class, I typically don't like using parentheses for these polar coordinates. I typically use brackets just so you can tell they're different. You can tell they're polar coordinates. It's just a different way of locating the same location. And look at my picture, you guys. Be lazy. If this is B and this is A, what can you say about the length R in terms of A and B?
A squared plus B squared.
Square root of A squared plus B squared. This is why when I saw my X squared plus Y squared, I can interpret that as R squared. What do you think you can say about theta in terms of A's and B's? Just panic and say something. The tangent of it is B over A, or in this case, Y over X. Go in the other direction. You just showed me how to convert from rectangular coordinates to polar coordinates. Let's go backwards. Let's convert from polar coordinates to rectangular coordinates. If you already know what theta and R are, how would you use those to come up with X?
R cosine theta and R sine theta.
I agree. Because when you take a peek at my picture, plotting your theta, its cosine is going to be nothing more than the ratio of the adjacent side to the hypotenuse R, but that just, I said ratio. But that just simply means A is equal to R times the cosine of theta. It's exactly what I wrote here with the first equation. Okay, so I blew it. I called it X instead of A. I'm using them interchangeably. You guys, I don't like my example. It's too. There you go. I hope I have some more interesting ones.
What's the hardest one you have?
You want to?
Yeah.
You just write everything you have on paper up. Even if you don't do them all.
Yes, I'll be glad to do that. Remind me at the end.
Or just have them like scan them and then like, send them to us. Canvas, I'm sure they're. Text us, You also gotta remember you have a bad phone.
I have a what?
I said you have a bad phone. Can't expect you to text
No,
me.
like last year, this is a new phone. I walked in the Mass Center and a tutor said, "Wow, Professor Balica, you upgraded to 2004." It's just a phone.
That's okay, my parents have a sliding phone.
Yeah, that's like what you have.
Does that say?
It's still cool.
Yeah. Jitterbug's a dance.
They have the big old people phones. They had like those big old letters, or the big old numbers.
You guys make me feel so bad.
You've never seen that commercial?
No, I know that Jitterbug's a dance that my parents used to do. I'm sure that was fun. Well, I'm just saying, you guys are about the same age, so it would make sense, right?
I got an idea. Look at that region. What does that look like?
What?
What does that region D look like?
All it looks like is it's just bounded by one
By-
cosine graph.
No, by.
Oh,
by-
yeah, by that point, in the other corner. By that, what are you looking for, curve?
It's a value of a radius, right? So that's a curve
It's a
by,
line.
Yeah.
It's a cardioid.
Thank you. I sure hope I walk in the right class with it.
No.
Do we have to draw those? 'Cause, like,
wait,
Get to draw them. And I want you points for it. Oh. What's this one look like?
What?
What's this one look like?
that's,
Cosine, wait, we can't put
I really can't hear.
cosine.
Well, what's that thing? What's this polar graph look like?
it's a circle
It's a
with
circle.
radius 3.
Is that just like a big old circle? But it's like.
It's a radius 3 circle, right?
Radius.
Root 3.
Radius.
I thought it was
Approximation of the circle. I was thinking cosine of 3.
radius 3 halves. How did you get the 3 halves?
How do I get to 3 halves?
Yeah.
Okay.
Oh, yeah.
It's 3 all the way across. It's a diagonal.
Circle is radius of treehouse. Center's located at, did I make a mistake? I did, shoot. Center's located at 3 house, 0. Which is exactly what we did in my picture.
So we're supposed to just do that in our head, or are we just supposed to?
You guys got so much practice with this back in trigonometry, didn't you?
Not particularly.
Really?
No, that was a small part of
You're
trigonometry.
not gonna like the homework set.
That was like one day.
pretty easy. You only did it with
It was probably about a week.
And I think in my picture, you guys, in my picture, I guess that would be outside the cardioid, but inside the circle. Anybody give me a really nice application of a cardioid?
A heart.
That's a pretty one. Yeah, welcome to the Guitar Center. Microphones. Well, there are a lot of microphones designed in a cardioid fashion, so that when you're pointing towards you, you can receive the signals, but pointing towards the crowd, you're not getting anything at all. I'll stop. Anyway, come in. Let's set this up. Setting up, unlike my last example, you know what, you guys? This time, unlike my last example, I don't think my arc bounds of integration are going to be constant. After all, if I draw in here an arbitrary red ray emanating from the origin through the shaded region, I think it might look like that. And I think the outer bound of integration is determined by the circle, whose R values are given by this particular function in theta. But the initial point is error no matter where it is in the shaded region emanating from the origin. The initial point lives on the cardioid, where R is equal to 1 plus cosine of theta. Oh, you know what? I forgot what was in the integrand's position. That's just 1 over, finish it up.
Couldn't you simplify that though?
Oh, absolutely, I
Just
will.
get rid of the R's?
Yeah, they cancel. Is it?
Go two
Thank you.
times, two
I-
times.
Oh,
You
you're
can't
right.
know.
If you
Yeah.
want, I can split this up and just do half of it. As long as there's symmetry with everything. But you guys, to find those, the extreme values for R, for theta, excuse me, I'm talking too fast. I think I've got a bit of work to do. I think I need my eraser. I think I need to pull out a nifty piece of scratch paper. And I need to see where the R values are equal to each other on the graph of those two polar graphs. And so I will set 3 cosine of theta.
Wouldn't it be just pi over 4 and 7 pi over 4?
Say that again,
Pi over 4 and 7 pi over 4?
one more time.
You gonna third time's the charm, or did I have it wrong, or what?
Yeah, I just want to correct the answer.
What?
I just want to correct the answer.
Oh,
Not all
plus
the
or
others.
minus pi over 4, it's the same thing. Isn't that it? Oh, shit. Oh, shit, no wonder why.
Jeepers.
Excuse my language. Pi over 3.
I can't hear you.
Pi, isn't it pi over?
My apologies. It is. I was getting pi over 6.
Oh.
I just put my foot in my mouth.